So today we're dealing with mirrors, okay, and the law of reflection. So first of all, to start with mirrors, I want you to read about Vignalia, a village located high up in the Italian Alps, and they have limited daylight there during parts of the year. So in your notes, explain how a mirror helps but does not harm the people of the village, okay? It's really interesting. I'll also try and find a video and post that as well. So we want to work on the law of reflection. You've probably seen this in action if you've ever played pool or billiards. Okay, so we're gonna have to learn a couple terms here. All right. So first of all, this is our mirror down here. That's our mirror. Okay, and these little lines right here just show that this side is the reflecting surface and this side isn't. Okay, now I've drawn in this line right here. This is called the normal. Okay, the normal, as you can see, is 90 degrees to the surface of the mirror. And lastly, we have a ray. This is called the incident ray, because it is incident or hitting the surface of the mirror. And how do we know this? We draw a little arrow on our ray. So now if this is the incident ray, then this angle, okay, measured from the normal, and this is the important part, is called the incident angle or the angle of incidence. Okay, but for short, it's a theta with a subscript I. Now, when that ray hits the surface, it reflects, and if I had a protractor here, I'd do this exactly, but I could just eyeball it. It's going to bounce off just like a ball, and we indicate with the arrow that it's going now in this direction. So here, measured from the normal to the ray, is the angle of reflection, and this is shown with a lowercase r in your textbook. So this is the angle of reflection. And this is the reflected, if I could spell, reflected ray. Okay, so the angle of incidence equals the angle of reflection, and that's the law of reflection. But there's still a bunch of terms that we need to learn, and we'll use these over and over and over again. Okay? So, sorry, mathematically, what we just say is usually theta I equals theta R. This is the mathematical relationship for the law of reflection. So we can actually use this idea to locate images in mirrors. Okay? Oh, and there's another word, image. So some terms that we need to go over are image, okay, if you want optical device, and I'll go through all of these. We already have incident ray and reflected ray and incident angle and reflected angle. We have that in our diagram. Okay, and we have the law of reflection, and we should probably write that out. Law of reflection, okay? These are all terms in your textbook in bold, so you can do that, I think, yourself on page 418. All right, and I'm going to work on with you with finding an image in a plane mirror. Okay, and plane is just another word for flat. Okay, a plane surface. This paper is a plane surface. All right, so plane mirrors. Okay. So the first thing that we need to know about is an image. Okay, an image is a reproduction of an object. Okay, but there are real images and there are virtual images, and right now we are going to deal with a virtual image. Okay, so we're talking about rays of light. The reason why we see things is because light reflects off of things. So a virtual image is an image formed by rays of light, okay, that do not actually pass through the location. Where the images form. Now, what do I mean by that? Hopefully when I start drawing ray diagrams, you'll understand that a little bit better. But essentially, when you look in a mirror, okay, you cannot physically, the rays of light actually are not where the image is. Your eye thinks they're there, okay? Just like how when you put a penny in the water, and if you've seen or if you've walked through water and the things at the bottom of the river or water appear, closer, and we're going to talk about that as well. Okay, so we're going to be drawing some images here to figure out, and I'll explain to you where that is, where the image appears in this virtual image. So here is a mirror, okay, and I could put those little lines here just to show you. Okay, that's the mirror, but we tend to draw too much stuff, and then I feel like the picture gets, confusing. So we could draw a simple image here, or sorry, a simple object. So I like just to draw like a tree because it's easy-ish to draw. But essentially what I want to do is when you look in the mirror, okay, I want to show where this tree appears on the other side. Because when you look in a mirror, you're like, oh, you can see yourself. Okay, and there's an easy way and then there's the more complicated way. But essentially, what we want to prove, okay, and I think hopefully you know this, all right, is that the image, when you look in a mirror, appears the same size right? The same size. All right. So if you look at your face in the mirror, you see it as the same size. You see it as upright. Okay. And I'll explain to you how it's virtual. Okay. Same size has to do with magnification. All right. And we'll explain this to you. Oh, yeah. And it's the same distance into the mirror. So if you walked back from a mirror, it appears that your image is getting further away from you. And if you walk closer, then it's closer. So they're exactly the same place. So same distance. I'm going to say into and put quotes around it. Okay. Okay, so let's do this. So what you have to imagine, and I know this is the hard part, is your eyeball. Okay, and these are my eyeballs. Okay, so like right there, your eye is over here and there's lots of rays of light. So, but we need to pick one. Okay, so I'm going to pick one random ray of light to choose. So I'm going to have it coming from the top because if I just do the top of the image and the bottom of the image, then I can fill in. All right, so a ray of light comes in. Your eye follows that ray of light to the mirror. Okay. Now I'm going to eyeball the normal. Okay. And now I want to measure that angle. Okay. And this is going to be the hard part. Okay. So here we go. 90. It's like It's almost 20 degrees. Oops, let's straighten this out a bit. Line it up. Okay, so what is it? We got 10, 20, it looks like 22. So that means that when this ray of light comes in, it's going to reflect off the mirror at an angle of 22 degrees from the normal. So there's 90, right? 100, 110, so that's 10, 20, and 22. No, it's hard for me to see this, and I don't want to bang my phone and knock everything here. So I'm going to remove that. Now, that angle was measured from here. So now this is my reflected ray. And it's going to go off like this. Now, I know my eyeball's up here, but you have to imagine that, I mean, your eyeball's back here and there's rays of light coming everywhere. Now, you don't know that light reflects. Your eyeball doesn't recognize that. So your eye thinks that the light is coming. Your eye follows along this line and believes the light to be coming from somewhere beyond here. So now I'm drawing this line with this ray. I'm extending this ray with a dotted line. Excuse me. Because this ray of light is actually not here, but my eye believes it is here. Okay? So I can do this again, but I'm just going to show you something interesting, because I think you can, hopefully you can imagine if you had a ball and you bounced it straight down, it would come straight up. So if a ray of light goes along the normal, it actually will go there and back. So this line right here is also one of these virtual rays. So if I shot a ray of light right along the normal, okay, so I'll do this. So we could call this maybe 1 incident, and this is 1 reflected. This would be 2 incident. Okay, this second ray, it would go straight, but it would also come straight back. So our eye, if I extend it, believes it to be coming there. Now, this would be the top of our tree because those 2 rays of light converge at the same point. So now, just to show you, let's see how far away that is. So, let's do it in centimeters. Why not? Okay. So here we are. It's approximately 3.5 centimeters. And here's a half. 1, 2, 3. 3.5 centimeters, which is what I predicted. It is the same distance into the tree. Or sorry, into the tree is into the mirror. So what essentially happens is there are infinite number of rays of light doing this, okay? And they're all crossing at this point, forming the top of the tree. And then this is happening all along here and doing that for the bottom of the tree as well. So I can do another ray at a different angle, okay, just to show you that that happens again. And I'll show you that this appears right down here. And I know this seems really complicated, and I'll talk about the easy way. All right, so let's take one from the stump. I'm going to try and do like a different angle, I guess. Though, isn't that interesting? It goes right back through there. So, isn't that funny? I'm going to pick this one over here. I'll just pick a random, maybe a little bit smaller angle, just to show you that this isn't a coincidence. So here's going to be another incident ray. Okay, it's going to bounce off, and I have to draw my normal because I have to know where to measure my angle from. This is going to be a small angle. I don't think I did a good job of actually putting the normal. I don't know if you guys can see that. If you zoom in, my normal and my ray actually aren't quite on the same point there. Oh, that looks not parallel. And these are all the things, if we do this on graph paper, it works out a lot better. So this is about 10.5 degrees. So 10.5 degrees. So this is where I'm measuring from. I'm measuring from 90. Oh, sorry, not 10. It's 5. 5. I was going to say that didn't look right. So I'm going to go from the 90. I'm going to go 5.5. Okay. And I'm going to draw in my reflected ray. Okay, so this was my incident ray. This is my reflected ray, and I'm going to follow my reflected ray backwards because my eye does not know that that light is actually reflected. It believes it to be coming back from here. And then I can use the same rationale that a line or a ray that travels along the normal gets reflected back, so we follow that back. Okay, now this would be the stump of my tree. So let's see if I did a pretty good job. I can, like I said, I had a couple little mistakes there, but that's okay. Where exactly did that come from? Here. So it's 3 centimeters, not quite 3 centimeters. Okay, it is, let's just pick a number here. Okay, so 3.8. So there's, so now I'm going to see, I can go here and go see if that is 3.8. I'll move it over there. Sorry, is that 3.8? Yeah. I think I did not do a good job on this one. I am off by about 4 millimeters. Okay, but it's good enough. Now that's the top of the tree and this is the bottom of the tree. Like I said, if you do this on graph or lined paper, it's really better because then you can see if your lines are all straight, and I'll start doing that with the other ones. I just didn't do that here. And also I can see here that my normal isn't straight. So anyway, you fill in the blanks. Now, you could keep doing this for a whole bunch of the tree, but I'm not going to do that. I can just fill it in and say, this is my image, and this is a virtual image because you can see all these rays. These rays are not really here. It's just that our eye thinks they are there. Now, that's the long way. Okay? The short way is to know that an image formed by a mirror is always the same distance into the mirror. It's always upright. So I realize that maybe you're memorizing these, but also you see this every day when you look into a mirror. You just maybe haven't, thought about them that exact way. Okay? So that is plane mirrors in a nutshell. So the next note is going to be on curved mirrors. Okay? And I'm just going to maybe get my whole note in here if you want to take a minute and copy it. Okay. The next note will be on curved mirrors, and it is really helpful if you guys do this on lined paper. We'll have a bunch of other things to go over, but this is just a short note, and then the other one I will do it in a separate video. Okay. Thanks for listening, guys. Bye.